Okay, let's see if we can get started and roll into our fall break maybe a few hours earlier. Okay, so this is the Canvas calendar for the class. Here we are. We're, we're past the halfway point. And so today's Wednesday the 9th. And we're going to take a look at another way of looking at frequency response. Similar information, but just presented in a different coordinate system. So think about that. It's just a different coordinate system. We've been looking at Bode plots. That's one coordinate system. Nyquist is also a frequency response, but it's just in a different coordinate system. So today what I want to do is I just want to introduce the Nyquist diagram. This is not a diagram that you can draw by hand very easily. You can do a very, very, very rough sketch by hand, but we're going to try to get an idea of what it's about, try to understand what the information is on the Nyquist plot. It's really a piece of information that's best done with the aid of a computer. And so then I'll briefly review the Nyquist command in MATLAB. It produces that. The underlying theory of what it is in this chapter 9.2. I don't think you really need to study that theory too deeply. It's just if you, we do have a fall break, so if you want to spend a little bit of time, you could look at that, but I'm not going to ask any theory about it. This comes out of the theory of complex variables, complex analysis, about what it's about. What you really, I recommend you focus on is the next chapter, section 9.3. This is how we apply it to system analysis. And if you use the Nyquist plot, what you can do is you can determine whether or not a system is stable. And I'll explain this next week when we meet. So if you're going to do some reading, I would concentrate on chapter 9.3. Now, at the end of the chapter, there's a table. It's just a bunch of diagrams. And that set of diagrams basically help us understand what different Nyquist diagrams might look like. It plots both common Bode diagrams and also common Nyquist diagrams together, side by side, so you can see how they're related to each other. There's a set of homework problems that I recommend you take a look at over the next week or so. So we're going to be spending about a week looking at this idea of the Nyquist diagram. Okay, so that's where we are. Again, 9.2 is the underlying theory for those who want it, but really where the focus should be is probably chapter 9.3 and then 9.4. All right. So let me briefly review what we've been looking at. We've been looking at frequency response. Okay. Focus. There we go. The frequency response. Basically, we start off with a transfer function. We're given a model, g of s, in this class. And then so what happens is we let s equal to j omega. That's the concept of frequency response. So we get this function g of omega. Okay. Now, because this is j here, in general, this is a function which is complex valued. We call it complex. It's a complex result because we have j's floating around in here. So for example, if I have 1 over s plus 2, then the frequency response is 1 over j omega plus 2. This is a complex number. Okay. Now what we've done is we have in the Bode diagram, what we do is we plot the magnitude of g of omega versus omega. Okay, this is frequency. And we also plot the phase of g of omega versus omega. Okay, so we get two plots. Okay, this is what we reviewed. Okay, we did this on the previous exam. You get two plots.
We label them this way. This is the magnitude in dB. Okay, we do this in dB. And this is frequency. And we get some plot that looks like this, maybe. And then we have another plot, which is we call the phase of G versus omega. And it may do something, like this. Okay, these are two plots. This is the frequency response. This is the Bode diagram. Okay. Now, the Nyquist plot is similar information, but it's plotted a little differently. See, we take a look at this thing. This is a complex number. Another way to look at the frequency response, it's another coordinate system. And the coordinate system that we could do is I could plot on this axis, I could plot on this the real part of G of omega. And on this part, I'm going to plot the imaginary part of G of omega. All right. So rather than plotting magnitude and phase as functions of frequencies in two different diagrams, what we have here is we just have imaginary versus real. So this is imaginary versus real. Okay. So this is called the Nyquist plot. This is called the Nyquist plot. Okay. So you would have to have some sort of computer program, for example, that takes this and calculates the real part and imaginary part. You make yourself a table. Make yourself a table. So for example, we have omegas, 0, 1, 2, 3, like this. And then what you would have to do is you would have to calculate the real part of 1 over j omega plus 2. Do that on a computer. And then make another column. Say the imaginary part of 1 over j omega plus 2. You stick it in here, stick the number in. So for example, if I stick in omega equal to 0, I'm going to get 1 over 2. So the real part is a half. If I stick in omega equal to 0 right here, this is purely, it ends up, the imaginary part is 0. So I have 0.5 and 0. So I would plot that right here. 1/2. That's just for one data point. Okay? And then I'd have to do that for another data point. Let me stick in another data point that I can do in my head. Let me do omega equal to 2. If I stick in omega equal to 2 over here, then I get 1 over j2 plus 2. And this thing is going to end up being something like square root 2 over 2, square root 2 over 4, I think. And this is also going to be square root 2 over 4, but with a minus sign. So there's going to be some point down here. All right, and this is for omega equal to 0, omega equal to 2. So you can see this is going to be kind of a tedious process. There's no clean way to do it by hand. So it's done by computer. Right? This is done by computer. This is one interpretation of the Nyquist plot. It is imaginary versus real. Okay? Do this by computer. Okay? Do it by computer. Don't try to do it by hand. So let me tell you how MATLAB will do this. In MATLAB, let's suppose now our problem if g of s is equal to 1 over s plus 2. I would first describe g, and we'll do this on Monday. By the way, Monday, let's go to the lab on Monday. The transfer function, the numerator is 1, and the denominator is s plus 2, like this. And then we simply say Nyquist of G. And that would generate the Nyquist plot. That's it. Very simple. What would probably be helpful is when you do the homework problems, there's homework said there. I recommend you try this for homework. One of the things I ask you to consider is to compare the Bode and the Nyquist. compare the Bode and the Nyquist plots. And one way you can do that kind of side by side is open up two figure windows. Open up two figure windows. And you might do this. Say figure 1. That puts it in the figure 1 window. Bode G. And then put another comma. And then say in figure 2, do Nyquist G. Okay, that gives you two windows. This is window 1, and this is window 2. And then you can put your two windows side by side, and you can take a look at that. Do those homework problems, and this basically allows you to create your own table 9.3. 9.3 is in the textbook, but you could dream up some transfer functions of your own, and then do this, put them side by side and take a look at them, and then you can create your own version of what is in the textbook, table 9.3. Okay? Let me go ahead and sketch a few Nyquist plots right now. Let me pretend I'm going to do some table 9.3s, and let's take a look at some features. We're going to take a look at some Nyquist plots and Bode plots. The first example is, let's go ahead and do g of s is 1 over s plus 2. Okay. If I do the Bode diagram, this is what I'm going to do. I'm going to try to squeeze the Bode diagram right here. Okay, this is omega. This should be the magnitude in dB as a function of omega. And so the Bode gain is a half. A half, I think, is minus 6 dB. So it's going to start off right here at minus 6 dB. We'll draw a straight line approximation like this. It's flat, and then it falls off like this. And this slope is minus 20 dB per decade. The actual curve is something like this. Right? And the corner frequency here is at omega equal to 2. We can sketch the phase also as a function of omega. We'll label this as the phase in degrees. It's going to start off at 0 degrees and eventually go to minus 90 degrees. And the straight line approximation will look something like this. The corner is at 0.2 and 20. And the actual curve is going to look something like this. Okay. Magnitude and phase. Now, this is the Bode diagram. This is the Bode. Over here, let's do the Nyquist plot. The Nyquist plot will look something like this. If you do it in MATLAB, it's going to label this. It's going to label this axis. It's going to call this the real axis. They're going to put the label down here at the bottom. And they're going to label this axis. They're going to put the label over here on the side like this. So they're going to call this the real axis. And they're going to call this the imaginary axis. Okay, they're going to call it real and imaginary. Now, when I do things by hand, I label the arrowheads. I call this real and imaginary. Okay? But MATLAB is going to create a window, and it's going to label this window edge the real, and this window edge the imaginary. So think about what's going to happen again when omega is equal to 0. When omega is equal to 0, the number is a half, so it's 1/2 right here. Omega equal to 0 is equal to a half. Let's take a look and see what that looks like over here on the Bode plot. It's minus 6 dB and a phase of 0 degrees. Okay? So this is minus 6 dB and the phase of 0 degrees. So what that tells me is that this direction over here is the same thing as 0 degrees. Okay? This direction out here on the arrow is the same thing as 0 degrees. Now, what happens as frequency increases? As frequency increases, the magnitude gets smaller and smaller and smaller, which means I need to get closer to the origin. Okay?
I initially start off, the magnitude is a half. But as frequency increases, I need to get closer to the origin. But the phase also changes. I start off at here initially at 0 degrees, but as frequency increases, the phase goes eventually to negative 90 degrees. We plotted one of the intermediate points. We plotted omega equal to 2, and it was like somewhere like right here. I did that one point by hand. You can do that as well. But the computer is going to generate all the points, all the omega points, okay, all the points on the frequency axis omega. It's going to plot the real part and the imaginary part. So here we have magnitude and phase. Just convert magnitude and phase to real part and imaginary part, and that's what you get as the Nyquist plot. And so you get a plot that looks something like this. Okay? It's semicircular. It's a semicircle. And I'm going to put a little arrowhead like this. This is omega equal to 2, but I'm going to put an arrow on top of that point. And that arrow tells me that this means it's increasing omega. This is the direction of increasing omega. Okay? When omega is very large, when I have a large frequency, the magnitude is small, and the phase is negative 90 degrees. The magnitude is small, and the phase is 90 degrees. Now, when you ask MATLAB to do the Nyquist plot, it's going to give you this, but it's also going to draw this diagram. And I'm going to put it in with a dashed line. MATLAB's not going to put it in with a dashed line. It's going to just draw it in completely. This is G of negative omega. This is the negative frequency scale. Okay. The Bode diagram doesn't do negative frequencies. It only does positive frequencies. But Nyquist plots will do positive and negative frequency. This is positive omega, and this is negative omega. Okay. So another way of interpreting a Nyquist diagram, after we look at this, is that it is a polar plot. This is an alternative interpretation. This is an alternative interpretation of the Nyquist plot. Is to think of this as polar coordinates for the frequency response. Polar coordinates. Think of it as polar coordinates. And so for polar coordinates, what we do is we call this 0 degrees, we call this 90 degrees, call this 180 degrees, and so forth, okay? This is angle. Angle. This is positive angle. Now, a lot of our Bode diagrams, you notice for most real systems, the phase is going to be negative because it takes time for the system to respond. You put an input into the system, and it takes a moment for the system to respond. That's a delay, and that's expressed as a negative angle. And so negative angle would be this. This would be 0 degrees. This would be minus 90 degrees, and we call this minus 180 degrees, and you call this minus 270 degrees. So notice here, 180 and plus 180 and minus 180 are the same thing. So that's another difference between the Nyquist plot and the Bode diagram. On the Bode diagram, negative 180 degrees is down here, and plus 180 degrees is up here somewhere, and it looks like two different lines. And so there's some ambiguity there, some confusion. But in a polar plot, minus 180 and plus 180 are the same thing. Okay? So think of the Nyquist plot as being a polar plot where this is angle, and the distance here, the distance from the origin, this is the magnitude. This is the magnitude. Okay? So let me kind of summarize what is the Nyquist plot.
Nyquist plots the frequency response it plots the frequency response g of omega. You can interpret it as imaginary part of g of omega versus the real part of g of omega. Okay? Imaginary versus real. Or you can think of it as the magnitude of g of omega and the angle of g of omega in polar coordinates. Okay. One of the things you'll notice is there is no frequency scale. Okay. On a Bode diagram, if we come back here, there's a frequency scale. We've got 3 variables altogether on a Bode diagram. We've got magnitude, phase, and frequency. 3 variables spread across 2 pictures. Here we only have 2 variables, imaginary and real. The frequency, you really don't know. You don't know what frequency is along here. If I just give you a curve, you just know the frequency goes from 0 to infinity. But where is omega equal to 10? You can't tell. Where's omega equal to 1? It's not obvious. Okay. So there is no frequency scale. The other thing that you should note is that we plot it for both negative and positive omega are plotted. Okay. And what you should notice is that these things are symmetrical. So there's really no additional information. This is symmetrical with respect to the real axis. Okay, the Bode diagram doesn't show the negative frequency. It shows you only the positive frequency. But there's really no new information. It just kind of completes the picture. Okay. Let me do a few more examples. Let's do example number 2. This is a second order system. Okay. Let's sketch both the Bode diagrams and the Nyquist plot. So split the page in half. We'll put the Bode over here, and we'll put the Nyquist over here. All right. The Bode diagram is 2 pictures, magnitude versus frequency. Magnitude versus omega. And phase versus omega. Phase in degrees. 2 diagrams, 3 variables. The Nyquist plot has only 2 axes. So I can think of it as polar coordinates, 0 degrees, minus 90 degrees, minus 180. Or I could think of it as imaginary versus real. Either are correct. Both are correct. Either one can be used. Okay. In the Bode diagram, the frequency axis is clearly labeled. Here, we don't see frequency. All right, so this thing, if we do a quick sketch, the magnitude, when omega is very small, it's 1/10. Okay, the Bode gain is 1/10. 1/10 is negative 20 dB. So it's going to start off here at negative 20 dB. Straight line approximation does this, and then it falls off. And this slope, being second order, is a minus 40 dB per decade. And this corner frequency is square root 10. And the phase is going to do something like this. It's going to start off at 0, and it's going to eventually go to minus 180 degrees. Okay? So here's the straight line approximation. The magnitude, this damping is a little bit small. It may have a little bit of a peak here, so it may do something like this. Okay. Get a more accurate picture, just go ahead and enter that into MATLAB and ask it to do the Bode plot for you. Put it in figure window 1. We'll put this over in figure window 2. So what we could do is we could take this information, magnitude and phase, and just take point by point, start off at low frequency, pick a magnitude and phase pair, and plot it over here as magnitude and phase in the polar coordinates. So I could start off here at low frequency and say when the frequency is low, I've got minus 20 dB as the magnitude, so that means my distance from the origin should be the equivalent of minus 20 dB. And my phase is 0 degrees, so I got to be out this way. And so it starts off right here at 1/10. Okay, that's one easy point to figure out. The other easy point to figure out is when omega is very, very large. When omega is very large, the magnitude is small. That means I need to be close to the origin. When omega is large, I need to be close to the origin. But the phase is minus 180. I need to be approaching from this direction. Okay? So I need to go from here to here as frequency increases. I need to start here at omega to 0, and as omega increases, I need to get here. But I need to start approaching from the minus 180 direction. And so this is the picture that it looks like. My artistry is not very good. It looks something like this. Okay? It goes something like that. Now, if we look at the note earlier, I said what we have to do to do a complete Nyquist diagram is we also have to plot it in for negative frequency. Negative frequency is not on the Bode diagram because it's really not additional information, but it's a little bit helpful in the Nyquist diagram to see it. So we're going to put in the negative frequency. We're going to do like this. Okay. So again, my artistic abilities are poor. These are supposed to be symmetrical. Should be the same. So this is from minus infinity to 0. Okay, let's put a little arrowhead right here. It goes this way and this way. Okay, as frequency increases, I got negative numbers, omega, negative omegas. They're getting closer and closer to 0. Now omega is good to 0. Now I got positive omegas, and it goes around like this. So it goes something like that. Okay? Let's do another one. Just 1 over S. We'll put the Bodes over here and the Nyquist over here. Okay. We're going to plot magnitude versus frequency and phase versus frequency. Okay, this is the Bode over here. So we know that this thing looks like this. And the slope is minus 20 dB per decade. As frequency increases, the magnitude just gets smaller and smaller. The way we should draw it is we should pick omega equal to 1 and make this line go through 0 dB. Okay. Because the Bode gain for this function is 1, 0 dB. The DC gain is infinity, but the Bode gain, we ignore it, and we just get a gain of 1. the phase is minus 90 degrees for all frequencies. So let's do the Nyquist plot over here. 0 degrees, minus 90 degrees, minus 180, so forth. Or you could call this the real and call this the imaginary axis. All right, so what we have is that no matter what the frequency is, the phase is negative 90 degrees. So all the points are plotted on this negative 90 degree direction. And what we see is that when omega is very small, the magnitude is infinite. Where's infinity on this? It's off the page. Okay? So we start off the page, but at negative 90 degrees. We start off the page down here. And as frequency increases, the magnitude gets smaller and smaller, which means I need to approach the origin right here. As frequency increases, the magnitude gets smaller, which means the magnitude gets closer to the origin. But the phase is still negative 90 degrees, so I got to stay on this axis. Let me maybe try a magic marker and see if this works. So that's what it looks like. That's the Nyquist plot for this function. This is for positive omega. For negative omega, we got this. Okay. Okay. Think of this as negative omegas. This is positive omegas. All right, so omega equal to 0 is way down here. Omega equal to 0 is way up here. This is omega equal to 0 positive is way down here. Here's omega equal to 0 negative is way over there. Okay, let's do another example. You're noticing I cannot draw really accurate diagrams. I can't sketch them because I'm not a computer, so there's not much detail. Okay? But let me, again, sketch these. Bode plots over here, and Nyquist over here. Got plot magnitude versus frequency. And here we'll put in phase versus frequency. There's 3 corners. Omega equal to 1, omega to 2, omega to 3. Okay, remember this is not linear axes. These are logarithmic, so the tick marks should not be evenly spaced. 1, 2, 3, 10 is right here. But we got, it's going to start off flat, then drop off minus 20, then to minus 40, then minus 60. Okay, so it's going to eventually go off at minus 60 dB per decade. It's a third order system. The Bode gain here is, let S go to 0 everywhere, I get 30 over 3 is 10, so it's going to start off at 20 dB. In the phase plot, it's like 3 first order systems. It's going to start off at 0 degrees and eventually go to minus 270 degrees. See, the relative degree of this system is 3. I got 3 poles, no zeros, so it should end up at minus 270 degrees. And so it's going to do something like this. Okay, it's going to end up at minus 270. Let's see what the Nyquist plot would look like. We'll call this 0 degrees, minus 90, minus 180, minus 270, minus 270 degrees. Okay. Think of this as real part and imaginary part of G. Real part of G, imaginary part of G. Okay, you could use MATLAB to calculate this, or you could make an Excel spreadsheet, use complex numbers in Excel and calculate it. The easy points to calculate would be omega equal to 0. When omega equal to 0, at very low frequencies, I get 0 degrees with a gain of 20 dB. The gain of 20 dB is 10, so I should start off right here at 10. 10 at an angle of 0 degrees. This is omega equal to 0 right here. That's the one point that's easy to do. And what I see as omega increases is that the magnitude gets smaller and smaller. I need to get closer to the origin over in the Nyquist plot. As frequency increases, the magnitude decreases. My pen needs to get closer to the origin. Okay? But I need to approach the origin from the direction of minus 270. So this is what it looks like. This is the direction of positive frequency. And negative frequency is going to look like this. There we go. So this is negative frequency. Now, one of the things you will see that the computer will do is it's going to highlight a special point on the diagram. And that point is the point minus 1. And offhand, I'm doing this from memory. I'm just guessing. Actually, I don't have any memory of this at all, so I'm just taking a wild guess. Minus 1 is going to be at some point out here on this axis. Okay, the point, minus 1. Minus 1 is 1 at an angle of 180 degrees. This is a special point in system analysis, and we're going to learn about this on Monday. And because it's an important point, most programs that will do the Nyquist plot are going to highlight it for us. And MATLAB is going to do the same thing. And I think, and I'm taking a wild guess here now, I think it's going to be inside this little loop here. I think it's somewhere right here. It's going to put a little mark right there. And I think in MATLAB, this is a red cross. I think it's red. They're going to put a little mark there. Okay. On Monday, we're going to look at this picture, and then from looking at this picture and its relation to this point, we'll tell whether or not a feedback system is stable. This is not a feedback system. This is just a model. But on Monday, we're going to say, suppose that model or that system is inside of a feedback system, we'll be able to determine whether or not the feedback system is stable. So when you do Nyquist, you'll see this little thing highlighted. We'll talk about this on Monday. This is Monday's discussion. And I think for this system, I have a guess it's going to be in here. It could be out here, but it's somewhere on this real axis. All right? I didn't highlight it in the previous examples. In the previous example, minus 1 is going to be out here somewhere. Here's minus 1. Here, for sure, minus 1 is going to be out here somewhere because this is 1/10, and all this picture is kind of small. Minus 1 is going to be way over here. And in the very first example, let me see if I can find it. Again, here's a half. So negative a half is over here. So negative 1 is over here somewhere. So I know I can sketch those more accurately. But this one, without knowing more details about these points, it's a little bit difficult for me to figure it out. So I'm just taking a guess.
So don't be surprised when we do this example on Monday that if minus 1 is out here. This is my guess. This is my guess. It's right here. Okay, I'm just guessing this. All right? Okay, so there's some homework problems. I recommend you try them out on the computer. Use the computer. Please use the computer to do these things, to study them. And look at the homework set over the next few, in the coming weeks. So on Monday, let's be in lab. Turn on MATLAB, ready to go. And we're going to do some Nyquist plots. We're going to do Nyquist. We'll do some Nyquist plots, and then what we're going to do is also, the Nyquist plot is going to be able to tell us, we will be able to determine stability of a control system, a feedback system. Okay, so that's what we're going to do. Today we're just plotting this function as a function of frequency. On Monday we're going to put this thing inside of a loop and then tell us whether or not the system is stable. That's for Monday. Okay, you all have a good fall break.